Let's move over to Article 240. I love going to brand new articles. It just feels good that we finished up Article 230 and we're starting fresh on Article 240, overcurrent protection. Let's go to the scope of 240. Covers the general requirements for overcurrent protection devices and the installation requirements for overcurrent devices. You have type S fuses, Edison fuses, Carson fuses, knife blades, circuit breakers, GFCI type breakers, AFCI type breakers. We're not going to be covering all of these in the video, but they are covered in the textbook. Important before we go too far is to understand the definition of what overcurrent is. This is contained in Article 100. And as it says on the bottom then, current and excess of the equipment rating caused by an overload. That's putting 20 amps. Let's see, we can't really put 20 amps. Probably need to plug in two things in here, Mike, because that's the only way you could overload that. Right? Because if you plug in a regular attachment plug, is that right, guys? You can't overload something if you plug it in with an attachment plug that's rated for the attack. So, but if I put a 20 amp load on a 15 amp circuit, well, then I'm overloading the circuit. It also includes short circuits. That means it's a phase-to-phase fault. Or a ground fault, which means it's phase-to-phase or phase-to-neutral fault is short circuit. And a ground fault is going to be phase to enclosure where that fault current is going to return back on the source. So this is real important. Theory is so important to understand the code. Article 100 is important to understand the code. The structure 90.3 talking about chapters 1 through 4, 5, 6, 7, and 8, and the annexes, and how that's all important. And then you get down into the small terms. The definition of overcurrent is important because we're going to be using this in 430. We'll be using this in 440. We'll be using this in 240. We use this so many times. Matter of fact, we already used it in 230-90, and we just kind of like let it go. And I felt, let me let it go. Because, see, in 230, Ryan, do me a favor. Read me what it says in 230-90. Does it use the word overcurrent protection? What does it say?
Each ungrounded service conductor shall have overload protection.
Overload protection. So we'd have to go to Article 100. Do we have a definition of overload in 100? Is there a definition of short circuit?
Definitely short circuit, I know.
Then let's take a look at. You guys can get your code book out to watch the DVD.
Yeah, I don't know. Never mind.
Take a look at it, streamers, and find out. Let's get into the detail here. So, is there a definition of overload? Short circuit.
Maybe it's in 240.2.
I know there's a definition. I think there's a definition.
Yes, there is, Mike.
What does it say, Victor?
Operation of equipment in excess of normal full load rating.
Okay, so that's
got the alphabet.
So I need this graphic. I need to make sure that that's Article 100, right? There's a definition in 100 for overload, right? Is there a definition for short circuit in 100?
No.
Is there a
No.
definition for ground fault in 100?
Yes.
So that I need to identify this graphic that there's a definition of ground fault. Okay, so overload. Okay, Victor, read me the definition of overload.
This is just a part of it, but the first part of it. Operation of equipment in excess of normal full load rating.
Okay, we're going to stop right there. See, overcurrent protection. Let's go back to this graphic. If you're going to have overcurrent protection, you're protecting against what? Number 1, overload. Number 2, short circuit. Number 3, ground fault. At the service, and I'll go back to that one graphic. I think I'm going to go back to this graphic right here. Let's take a look at this graphic right here. This is the service disconnect means. Here is the service conductors, and I want to make sure service conductors, well, we won't have to hear. These conductors, this breaker cannot protect these conductors against short circuits and ground faults. It's the line side. Right. So I can't have this as the overcurrent protection because overcurrent protection means protection against overload, short circuit, and ground fault. So we're starting to get a little subtle here. Services, you can only have overload protection. Now, the overload protection, which is the service disconnecting means, which is going to be more than likely incorporated within the service disconnecting means or adjacent right next to that here, that overcurrent protection becomes what? That overload protection for the service becomes what? The feeder short circuit ground fault. It becomes the overcurrent protection for the feeder. So it's an overload protection for the service because I can't protect the line side for short circuits and ground fault. But the load side of that device becomes overcurrent protection for the feeder conductor. So subtle little point here, but we're going to try to keep hammering this in later on because it does become important. Let's move on to some definitions. I never really liked this graphic. You love this graphic? I guess I would like to see something different, but let's go with what we have here. A couple important things. You know what I could do right here? This is a perfect graphic to show me where I can run one service with a service point and run service entrance conductors over to the building disconnecting means, right? And run a separate set of service entrance conductors over to the PV system. Is that right? So all the red is service up to where? The main means a cutoff. After the main means a cutoff, I have now, which is going to be in black, it's going to be what? That's my feeders. Then I have the feeders, and I'm making taps on the feeders, and then I'm having overcurrent protection. Well, it doesn't really matter. I wouldn't call these feeders necessarily because, well, it's okay. It doesn't really matter because you can have taps here. This is a tap, and this is what I tell people. This gets kind of tricky. I tell people, look, you must provide overcurrent protection for conductors in accordance with 240.4. Either that, or you do one of two things. You're screwing up, or somehow you made what is called the law of compensating errors. You made enough mistakes that you actually got it to comply with a tap rule. So it's one of those two things. You're either going to make it comply with a tap rule, or you screwed up. Now watch how this works out. Here's what a tap is. By the way, when you make connections to the service, that's not a tap.
Right, that's correct.
Taps can only occur on feeder conductors. So here are my feeder conductors. Now watch this. I've never done this before in a class. Ready for this? These smaller conductors that are being connected as a tap, you have to terminate the tap conductors in an overcurrent device. So that's number one. You're going to have to terminate them in an overcurrent device. And that overcurrent device you're terminating into, is it providing overcurrent protection for the tap? No. It can only provide what? Overload protection. So this is going to be overload protection for these tap conductors. But how do we protect the tap conductors against short circuits and ground faults?
By the upstream device.
By the upstream device. And the way we can get these conductors protected against short circuit and ground fault by that device is to have restrictive conditions in what you can do for these conductors. If you, hey, listen, I'll let you run that wire and not have short circuit and ground fault protection directly, but allow a device larger than that as long as you limit the length of the conductors, you terminate it in an overcurrent device, you size it a certain manner. So watch what we're doing here. These conductors, which is the tap conductors, will be provided with overcurrent protection, which means what? Overload, short circuit, and ground fault. How to achieve that? This overcurrent device right here gives me overload protection. This device upstream gives me short circuit and ground fault protection if you comply with the rules. So let's go into the rules. So I guess, I really love this graphic. Let's go to 240.4, protection of conductors. I'm having fun now. I love this part of the rule. Here we go. Basic rule is this. Conductors, except as permitted in 240.4a through g, must be protected against overcurrent in accordance with their ampacity. I have a problem when the code does this, and it's not the code's fault. I hate it when it say you have to do this except as permitted in A through G. I would rather you have an A, a B, a C, a D, a E, an F, a G, and an H. In other words, if it's not A, B, C, D, E, F, G, then it becomes an H, which is what? All other conditions. Because when you don't do it that way, then people think that you have to have this rule. They forget except as permitted through A through G. So what do you have to do? You must protect conductor at their ampacity, except as A through G. So now we got to look at all the different possibilities in A through G. But let's look at this graphic first. I have, what do we have here? 1/0 wire. I guess it's 75 degrees C in table 31016B16. It must be rated 150 amps. I put it on a 150 amp breaker. I comply with the rule. I protect that wire at its ampacity. Let's go over here. I have a 50 amp breaker here. It looks like 2-pole 50 amp breaker. Okay. I'm running 8 gauge wire. I go to table, oops, sorry about that. I go to table 31015B16 at the 75 degrees C, only assuming the terminals are rated for 75 degrees C. So I need to make sure that I look at the graphic, the text. Let's make sure I look at the text and make sure that I specifically, watch this. I have to specifically say that the terminals are rated for 75 degrees C, and that's a fact for me to size the conductor to 75 degrees C. If not, and I got to be careful in all my examples and all my graphics and all my text, that I cannot use the wire under 100 amps the size of 75 degrees C unless I qualified it in the statement. Assuming that the terminals are rated for 75 degrees C in a circuit, then what size wire would you use? So assuming the terminals are rated for 75 degrees C for the circuit, then if I have a 50 amp breaker, I could use an 8-gauge conductor. Okay, well then it means 8-gauge wire is rated 50 amps at 75 degrees C, 50 amp breaker, that complies with the basic rule. So we're good there. That's the basic rule, except A through G. Let's see what we're going to have here. Let's go to B, which is the next size up rule. He says, yeah, I know what A was talking about, but look, the general rule. Where the conductor ampacity doesn't correspond with the standard overcurrent device rating, then you can use the next higher rating device if it doesn't exceed 800 amps. Well, 500 kc mil, it's rated 380 at table 31015B16 at 75 degrees C. We do use 75 degrees C, so we're good here. And, well, you know what? 380 amp wire, yep. It doesn't correspond to standard size. 240.4B3 allows us to go to the next size up breaker. So whenever the ampacity doesn't correspond to standard size, which is really, really common. I mean, you go to 75 degrees C column, you start looking at the conductor ampacity, you know, you go to, the problem is this. Ampacity is per Article 100. 100 says the ampacity of a conductor is under the condition of use. When you're really finding out the ampacity of a conductor, you go to table 310.15, you go to 310.15b, and 310.15, I think it's B2, tells us that the ampacity can be adjusted based upon correction and adjustment. Correction because of temperature, adjustment because of bundling. And whenever you adjust the ampacity of a conductor per Article 100, you use the insulation rating, and since we're using 90 degrees C wire for all practical purposes, we get the ampacity at the 90 degrees C, we adjust it and we correct it, and then we get the new ampacity. So now when you get the new ampacity after you adjust it and correct it, pretty much it's not going to correspond to a standard breaker as listed in 240.6. And because when you correct and adjust ampacity, it doesn't correspond, the rule says this, I'll tell you what. If the ampacity conductor does not correspond to the standard size rating of an overcurrent device, you can use the next size up device. So the general rule is you probably are going to always be using the next size up device. That's assuming that you're not supplying multiple receptacle outlets. That's what 240.4b talks about. So we do a calculation. It doesn't correspond to standard size. We go up to the next standard size per 240.6 as long as we don't exceed 800 amps. Now, there's been proposals to allow that to go up to 1,000 amps or 1,200 amps. Well, Mike, why do you allow it to go next size up? Well, Eric and Victor, you guys talked about this, saying, well, you know, the ampacities are not quite as absolute. You know, like, oh, my gosh, you put 21 amps on a 20-amp breaker. What's going to happen? It doesn't work that way. But you randomly, you kind of get a number. You say 20 amps. And so if you got 380 amp wire, the calculated load can't be more than 380 amps. You put a 400 amp breaker inside there. What could possibly happen? Short circuit, ground fault, device opens up. So it doesn't really matter why. If the ampacity conductor doesn't correspond to standard size, next size, we're good. Move on. Here's an example in PV. This is a big deal in the PV industry. These guys are having all kinds of wires up on the roof. They're bundling conductors, a lot of things happening up there. So the ampacity conductor is always going to be adjusted and corrected. Now, I'm not going to talk about PV, but in PV systems, many times overcurrent protection might not even be required. But it's only where overcurrent protection is required that we have to be worried about this rule. Here's an example of 240.4c that you cannot use the next size when you are over 800 amperes. So here's a 1,200 amp device. Well, if you can't use the next size and you got a 1,200 amp device, well, then you need 1,200 amp wire. And if you're going to parallel this in 3 raceways, then you take 1,200 amps of capacity required, divided by 3 sets of parallel sets, gives me 400 amps per set. I have to go to 75 degree C column. I don't go to the 90 degree C column for size of the conductor. Remember, that was 11014C1B. 11014C1B says over 100 amperes, you size the conductor to 75 degrees C. You size them at 75 degrees C. But Mike, a minute ago, you were just talking about the 90 degrees ampacity adjustment. I know it gets kind of complicated, but no matter what you do, you size the conductor 75 degrees C. Then if you have correction and adjustment, you're going to use the 90 degrees C ampacity for that. And after you do that correction and adjustment, you got to make sure that that ampacity takes care of the load. You have to make sure that that ampacity can be protected by the overcurrent device. We're slowly starting getting a little bit more complicated. I'm building ourselves as we get closer to 310.15. So let's go back to this graphic here. I'm sizing the conductor 75 degrees C. I take 1200 divided by 3, 400 amps per parallel sets. I go to table 31015B16 at 75 degrees C, 600 kc mils per conductors. That's what I have to do. Now, Eric, we were just having a conversation this morning. You were saying that you were talking to a cable manufacturer. Was it DLO cable? What kind of cable did they list the wires as MCM?
Yeah, it was the cables that are specified in Table 400.5B. You know, the highly flexible cables, highly stranded Class K, Class M stranding, stuff like that. And as you said earlier, one of these cable manufacturers, they say they do it 90 degrees C free air. Okay, but yeah, I'm calling some of these cable manufacturers, 2 of them actually, and I say, well, I need a price on 500 kc mil. They say, well, we don't have kc mil, we have MCM. Okay, give me a price on 500 MCM. You know?
What Eric is saying is some of you guys are like, there's something I'm missing here. And I'm usually that way because these things happen around me and I don't know what's going on. What Eric is saying is this. He used the word MCM. Years ago, we didn't call them kc mil conductors. They're MCM, 1,000 circular mils, right? It was with Roman numeral, MCM, right? So it's 1,000 circular mils. And then wait a minute, 1,000 is K, right? So it's a kc mils, okay? And so that's the one thing that changed inside here. But when we were doing MCM, here's how it used to work. 400 amp service, 500 MCM. 800 amp service, 2 sets of 500 MCM. 1,200 amp service, 3 sets of 500 MCM. It was always wrong. Here's the deal. 400 amp service, 1 set of 500 kc mils. 800 amp service, 2 sets of 500 kc mils. 1,200 amp service, 3 sets of 600 kc mils. Because the ampacity of each of the parallel sets cannot be, when you add them all up, they cannot be less than the rating of the overcurrent device. Okay? Let's move on to the next one. Here's another rule. Small conductor protection. This is the one that many people think that the ampacity of a 14-gauge wire is rated 15 amps, and a 12-gauge wire is rated 20 amps, and a 10-gauge wire is rated 30 amps. No. That's not the ampacity. That's just the setting of the overcurrent device if you comply with 240.4D. But watch this. 240.4 says that the ampacity of a conductor must be protected in accordance with 240 with its ampacity, except as A through G. Then when you get to 240.4D, it says that you have to protect these conductors in accordance with the following ampere rating, except as permitted through 240.4E or G. So take a look at this. So you have to provide a 15 amp breaker on 14-gauge wire, a 20 amp protection rather on 12-gauge wire, a 30 amp protection on 10-gauge wire if it's not E or G. Well, what's E or G? G is air conditioning. When it comes to air conditioning loads, it doesn't work this way. You size the overcurrent protection for air conditioning and refrigeration equipment in accordance with the nameplate. If this nameplate says 40 amp protection, 23 amp wire, well then I would put a 40 amp breaker and I would find some wire rated 23 amperes at 60 degrees C, and this is where people go nuts. I would run a 12-gauge wire. Mike, I thought 12-gauge wire was only good for 20 amps. Never was that. What the rule said is the maximum overcurrent protection for 12-gauge, not within the conditions of 240.4G. What was it? Back to the slide here. E or G, then you'd have the 20 amp protection. But when you get the air conditioning refrigeration equipment, you size the conductor. Again, this is not over. Let's see, this protection device right here is not overcurrent protection. See this device right here? This device is now we're starting to split it up. This is short circuit protection. This is ground fault protection. You can't protect a 40 amp breaker for 12-gauge wire and provide overload protection on that. You can't do that. How do you do that? The equipment itself has overload protection. If you take the equipment overload protection and you take the breaker, which is a short circuit ground fault protection, that protects the conductors and the equipment against overcurrent, short circuit, and ground fault. So now we're learning that overcurrent protection is not necessarily one device. Sometimes it's two devices. The tap rules are going to provide short circuit and ground fault protection, and you have overload protection. The service has no short circuit and ground fault protection at all. We just simply have overload protection. Air conditioning, 40 amp breaker, 12 gauge wire. The breaker is not providing overload protection. It's providing short circuit and ground fault protection, and the equipment has internal overload protection, and the overload of the equipment, short circuit and ground fault protection of the breaker. That's why a 40 amp breaker is perfectly fine on 12 gauge wire, because if the 12 gauge wire shorts out, it's going to create significantly greater current than 40 amps. Opens up the 40 amp breaker. If there's an overload, the overload of the unit does what? It turns it off. So that's why we're slowly working our way. We'll get the air conditioning refrigeration back in the 440 in a couple more DVDs. But I want to at least hit that.
Yeah, Mike, just want to make a mention that this is where it's important to follow along with your code book, because 240.4G is more than just air conditioning. There's a whole laundry list of items. There's a table in there.
Beautiful. So not only does 240.4D say you have to provide protection 15, 20, and 30, except permitted and E through G, then when you get to G, it has this huge list of all the, air conditioning, I'm sorry, you need to go to 440. Motors, I'm sorry, you need to go to 430. Let's take a look at 430. This is all part of G, but let's take a look at this graphic here on motors. Ryan?
If you don't mind me jumping in really quick before you go to motors, go back to air conditioners. So that air conditioner has, as part of the listing standard, the product standard, it has internal overload protection. If it starts pulling more than 25 or so amps, it's going to shut itself off. So we have ground fault and short circuit protection by the breaker, and the motor itself, the air conditioner itself, is providing overload. That is a very simple concept. If you haven't, and you need to understand this. If you can't understand that, you need to pause the video and ponder it or do whatever you have to do, because this part's as easy as it gets. Motors, same exact concept. I'm telling you, if you can lick the air conditioner, you got it. You've got feeder taps, you've got secondary conductors, you've got motors, you're going to have it all figured out. But unless you can accept this for fact, you are just going to be pulling your hair out and just ripping your skin off trying to get your head around motors. So understand this concept.
And what Ryan is saying is perfect. And what he's saying is you got one or two options here. Stop it like, I'm totally confused. I mean, wait a minute. Go back and listen again, and you're going to hear the same thing again. Believe it or not, if you play this back again, you can hear the exact same thing. Nothing changes, right? I mean, because we already recorded it. So, I mean, that's not going to change anything. You're still going to go nuts. So if that doesn't solve the problem there, say, you know what, I'm going to put a question mark on this. I'm going to make a note of this here, and I'm going to come back to later on. Let me go a little bit more into the code and get more confident knowledge, because we're going to cover this again in 430 and motors. We're going to cover this again in more detail in 440 and air conditioning. This is just a quick review in 240, but we're trying to set some stage here, that it's not quite what you might have thought it was going to be. And that's what Ryan's trying to say. But I want you to take some peace here. Take a deep breath right now. Stop. Let it go.
There it is.
There it is. All right. Let's go to motors. Again, quickly. You size the motor, you size the conductor at 125%. You got a 20 amp conductor. You go to 310, 15, B16 because it's a motor. We go to 75 degrees C, right? We had that 110, 14 C1, I think that was B. And so 10 gauge wire. But then the breaker size at 250%. Don't worry about the details. We'll cover this. It's no less than 55 amperes. It doesn't correspond to standard size. 430.52 C1 exception allows us to go up the next standard size. So we'd have a 60 amp breaker and 10 gauge wire. Mike, are you crazy? This breaker, 60 amp, is protecting these conductors and the equipment in the enclosure against short circuits and ground faults. Right inside here is a heater. And the overload is protecting the motor against what? Well, it's an overload protection. So you combine the short circuit ground fault plus the overload, then that provides protection. So that's the rules on 240.4. Let's go to 240.6, standard ampere ratings. This is an easy one. This is no thinking at all. This is just a table. This is just your standard ampere rating of fuses, circuit breakers. And we're going to be referring this all the time. We go back and forth and back and forth and back and forth. Matter of fact, I was looking at some slides last night that on air conditioning refrigeration, and we got to change some changes right now, because when we did the graphics on the slides, the numbers came out to be a certain number, and sometimes even we forget the standard rating of breakers. You know, they make a 50 amp, a 60 amp, a 70, 80, 90, some things that you might not expecting. Let's go to the tap rules. Okay, now we're going to get into the tap rules, 24021B. And I used to really be intimidated by tap rules, and I used to be really stressed out about that. I feel a lot more confident now, and I think I can deliver the information a little better than I might have done in the past. Let me see if that's true, if I can do that. Here we go. Ready for this? Except as permitted in A through G, overcurrent protection must be placed at the point where the branch circuit or feeder conductors receive their supply. If you think about that, whenever you have a conductor, you need to provide overcurrent protection where it receives the supply. But 24021 says the rule, provide overcurrent protection at the point they receive the supply. You drop in a breaker in a panel, overcurrent protection, you run your conductors. But there's lots of different possibilities when you would not be having overcurrent protection, or you can't provide overcurrent protection at that point. 24021, let's take a look at the graphic here that I love now. Service conductors, service equipment, feeder conductors, and tap rules. Now, these tap conductors, I'll just review it, have to terminate an overcurrent device, and the conductor of these tap conductors cannot be less than the rating of this device. So if this is a 100 amp breaker, then I'd have to have a 100 amp wire. Now, we have a 400 amp protection device here. Let's say with 400 amp wire, well, that 400 amp breaker is protecting the 100 amp wire against short circuits and ground fault, and then the 100 amp breaker is providing the overload protection on that 100 amp wire. Now, when you make a tap, here's a tap here. You cannot make a tap to a tap. So there's your rule. Except and permitted A through G, overcurrent device A through H, overcurrent devices must be placed at the point where the conductors receive the supply, and this is 240.21. So no tap to a tap. Let's get into the tap rule. Let's talk about the basic rule. Tap conductors must have an ampacity not less than the overcurrent device rating. Well, if you have a 100 amp, 150 amp breaker here, okay, then you need 150 amp wire. I mean, it's just that simple. Nothing less than that. You can't use the next size up rule. Here's the rule of 24021B11 on the 10-foot tap rule. Okay, you can have these conductors connect, have a lower ampacity, not have overcurrent protection at the point of where they receive their supply. If, number one, they can't have an ampacity less than the calculated load, which is kind of obvious, and not less than the overcurrent device that they're terminating into. So whatever this device is, this conductor has to have that ampacity. And you can see it's smaller than the feeder conductors we're making a tap from. Also, not only does it have to have an ampacity no less than the load, no less than the rating of the device, it has to have a certain size mass. This conductor cannot have an ampacity less than 1/10 the rating of the device. If I'm having a 400 amp device here, then these conductors cannot have an ampacity less than 1/10 the rating of the device. And if I have a 400 amp device, and the tap conductors must have an ampacity no less than the load, no less than the overcurrent device, no less than 1/10 of the rating of the overcurrent device, and if the overcurrent device that is protecting the feeder conductors that I'm tapping from, it's going to be 400 amps. Well, 1/10 of 400 amps is going to be 40 amps. Then you go to 40 amps? No. You go to 60 degree C column, you look it up, and you find out what size wire, and I think 40 amps is going to end up being at 60 degrees C. I'm guessing that's probably going to be an 8-gauge wire. That would be the smallest tap. It's just simply math, the way math works out. You know, we're not going to make it complicated. Let's look at some examples that Mike's put together for us here. All right. So we know it can't be less than 1/10, which means 8-gauge wire is the lowest tap on a 400 amp feeder. If I know the rating of this overcurrent device right here, let's say this device right here was rated 200 amps. Well, then my tap conductors can't be less than 200 amps. And I'd go to 75 degrees C column, and I believe 3/0 is rated 200 amperes. If this is rated 150, well, then it can't be less than 150. Then that would be 1/0 per table 31015B16 at 75 degrees C. If this was a 50 amp breaker, well, it can't be less then, well, it all depends. If that's, we'd have to make sure that in the example, we'll have to double check that example, that the text says that, okay, we're using equipment that's rated for 75 degrees C. Well, then I can size the wire to 75 degrees C. We just got to double check that, all those rules. Now, if you go past 10 feet, then sometimes you can't make a tap within 10 feet. Well, you know what? Think about it. There's not a whole lot that's going to change. If you go up to 25 feet, you still got to have the calculated load. You got to have the wire, have the ability of an ampacity no less than the overcurrent device you're going to terminate into, and you are going to terminate in an overcurrent device. The only thing that's going to change, like when you're running a little longer, so I think instead of doing the 1/10 of the rule, let's go with 1/3 of the ampacity of the rule. And that's what it is when it comes up to a 25-foot tap rule. Nothing else changes except it's going to have to be no less than 1/3 the ampacity. Let's run through these slides real quick here. 400 amp device, okay, not less than 1/3 the rating of the overcurrent device. Terminate in a single breaker or set of fuses rated not more than the ampacity of the conductor. So the following example here. Well, no matter what I do, if it's more than 10 feet, I have to have a minimum 133.3 amps. I'm not quite sure how I can round it off, but I'm just going to go ahead and choose to round it off at 133. There are no rules on talking about how to round off when you're not in Article 220, but we'll just use that 220 rule anyhow. So 133 amp wire is the minimum tap, but I'm terminating in a 200 amp device, so I can't, you know what? It doesn't matter what the calculated load is. Really, almost if you think about it, because you have to have an overcurrent device that's sized to the calculated load. Well, then once you size the overcurrent device, the tap conductors have to be equivalent to the overcurrent device. I mean, that just happens to work that way. And, of course, no less than the calculated load. If I have a 200 amp overcurrent device, regardless of the calculated load, assuming it's less than 200 amps, I need 200 amp wire. But it can't be less than what? 1/3 the ampacity of the tap conductor overcurrent device. So back over here. 200 amp main, I need 200 amp wire. 150 amp main, 150 amp wire. Let's say it's 100 amp main, 100 amp wire. Oops. If this was a 100 amp main, I have to use what? 133 amp wire. So that would be a good example. 200, 150, and 100. Yeah, I don't know if I have another graphic here or not, but that would have to be minimum 133. Now, outside taps. Now, you got to understand what we're trying to achieve here. We're really worried about wiring that's inside of a building. I mean, when you're outside a building, what can happen? You're not going to cause a fire. So when you're outside the building, the rules are a little bit different than when you're inside the building. It says this, outside the building, you can run that wire as far as you want to run it outside. We don't care. All we care about is that when you finally end, like any tap rule, you have to do what? No less than a calculated load. You're going to terminate in an overcurrent device, and it's going to have an ampacity no less than the rating of the overcurrent device, and that's it. So outside taps, now, or outside conductors, it doesn't even have to be well, I guess it's a tap. So it's a tap. Outside taps, no limit on the length of the conductor. Look at the graphic here. Make a tap, go as far as you want to. And then, of course, these are feeder conductors, entering a building. You have to have what? A disconnecting means. And you taught me, Ryan. It's either on the building or inside the building, but it's going to be nearest the point of entrance. And so this appears to be the nearest the point of entrance. And then I terminate into an overcurrent device, and I size the conductors. But there is no 1/10 rule. There is no 1/3 rule at all. Brian?
Well, I was talking with Ryan earlier, and correct me if I'm wrong, but it seems like a great use for this would be exactly what you're showing here when you're feeding a panel in an outbuilding or whatever, and you don't have any spaces left in your feed-through panel. You can use the feed-through lugs on the bottom of the panel that's got a 200 amp main and put a 100 amp main in your outbuilding, and you're good to go.
Well, look at it this way. A lot of times, and I hate to give examples off the top of it, because sometimes like, I screw it all up, but I'm going to give it a shot here. A manufactured home.
Yeah, well, exactly.
Okay. It has a main breaker in the panel.
Yep.
I'm outside the building. I have a main breaker outside that protects that bus, but instead of me putting a breaker for the manufactured home, right, I could put a smaller wire.
That was specifically what I was thinking about, park models.
There you go. I can put a smaller wire on the feed-through lugs because I'm making a tap outside, and then I can run. Also, another example of some taps, which is kind of cool idea. Let's say you have a 400 amp gear, and you have parallel lugs. Well, then you can run some 250 kc mills over to this one piece of equipment off of the lugs.
All right.
In other words, the tap doesn't mean you have to go with wire and then split bolt it together. It means that the conductors don't have the overcurrent protection as per the definition of 240.2. So I'm always, in my mind, and when I was an electrician, I never wanted to make a splice. Just never want to make a splice. So if I could come off a breaker, and if you're saying, like you said there, if I don't need to have overcurrent protection and I can make an outside feed-through lug connection with aluminum wire that's going to be 150 amperes to go into the inside panel, have overcurrent protection in the panel, well, then I'm fine, good to go. Ryan?
Yeah, if you're an electrician, man, embrace the tap rules. Don't let them scare you and don't let them freak you out. They're not that difficult, and you would be stunned once you put them in the front of your mind. You'd be stunned at how often you can use them. I had a friend of mine, this was when I was an inspector, he just needed a simple receptacle on the side of his house. Now, he didn't have any panel spaced outside. All he had was a 200 amp main, that's it. And his panel goes inside and everything's drywall, and he wants one receptacle outside of his house. So we called an electrician. He knew I didn't have a lot of time. And the electrician says, man, I got to go from the panel and up through the attic and everything else. I went there, looked at it for 2 seconds and said, here's what we're going to do. Little 30 amp feeder tap, boom, off of there, 5 feet, fuse, outlet, done, going home. That's it. Make a feeder tap. There's nothing to these. These things are a beautiful thing. Use them.
Yeah, and I think, but this is an intimidating thing.
Oh, yeah.
Until you read it enough times, like you said, you know what, stop it, go back, look at it again and again and again, and start thinking, okay, when can I run a conductor outside unlimited length whenever I want to and terminate into an overcurrent device inside the conductor to calculated load? When can I have a wire that doesn't have the ampacity? It's mostly because I don't have equipment I can connect to that I need to make connection. Taps they have some really, I tell you what, I think those of you in the electrical industry, and Brian, you said this to me, that you get EC&M magazine, and you don't necessarily read all the articles, but boy, are you looking at all those products. And I'm doing the same way. I'm looking at products and products. I go to trade shows. If you can, you get to a trade show, electrical trade show, go to it. And sit down with every vendor. I do a seminar all over the country. And when there's trade shows, guess what? I go to every single booth, and I'm looking around like, what the heck is that thing? And I'm like, wow. And so you're learning, and as you learn the products, you can make a tap in an enclosure. What do they call that thing that you can just kind of go on the wire and you just kind of...
A B-tap.
What is it called?
A B-tap.
Yeah. I mean, are you kidding me? You just go into the enclosure and you just kind of screw that thing inside there, and it just bites it right into the conductor, and without having to, insulate it, without having to do anything. This is some cool stuff, but that requires understanding tap rules, sizing it. 240.24, the location of overcurrent devices. Kind of simple, easy stuff here. Down on the bottom text. Overcurrent devices. Well, first of all, let's talk about readily accessible means capable of being reached quickly without having to climb over or to remove obstacles or without having to use portable ladders or use portable tools. That's Article 100. But 240.24 says it has to be readily accessible. Well, if it has to be readily accessible, and if you go to 100, that means that, you don't have to climb over anything. You don't have to move anything. There's no portable ladders. There's no tools. So this breaker right here, or this overcurrent device rather, is not readily accessible. Also, overcurrent devices must not be more than 6 feet 7 inches above the floor or platform. That is readily accessible. Locking does not have any effect on any of this. There's your 6 feet 7 inches, and the way you measure that is you measure from the center of the grip of the operating handle, fuse, switch, or circuit breaker, when it's its highest position, and it cannot be more than 6 feet 7 inches above the floor. So this is important because this nothing to do with readily accessibility. This has to do with the height of it. So that title needs to be changed. Now, there is a permission on 240.24A4 that you can have overcurrent devices located 6 feet 7 inches if it's next to the equipment that it supplies and it's accessible by portable means. Like, wait a minute, Mike, I thought you just said it had to be really accessible. Well, I know it had to be really accessible, but if it's next to equipment that's elevated and you had to get on a ladder to get to the equipment, well, it would be great if the disconnect, the overcurrent device that's next to the equipment above 6 feet 7 inches, that you had to have portable means to get to the equipment that you can turn off the equipment by the overcurrent device. So that is permission. That also is contained in 404. Ron, see if you give me that code rule in 404. Oh, it's right there. I'm sorry. It's 404.8A exception 2. talks about switches. See, 240 is talking about overcurrent protection. It can be located above 6 feet 7 inches if it's next to the equipment that it's supplying and it's accessible by portable means. But 404.8a exception 2 is talking about a switch. See, a circuit breaker is an overcurrent device, but a circuit breaker is also listed as a switch. And so therefore, the 404 rules, .8a, would also come in play. And it's fine. You cannot locate an overcurrent device near easily ignitable materials such as closed closets. Now, I did not talk about this, and I'm not quite sure whether we will, but there is a definition of a closet in Article 100. And so it would be used in 240.24d, and closets would also be used in 410, I think, maybe
16.
8.
16.
Is it 16? Oh, it was 8. The 16 having to do with, well, what kind of illumination can you, or luminaires and lamp holders can you put in a closet? Well, what's a closet? Well,
Clothes closet.
you want to tell us what a closet is?
Yeah,
Ryan?
it's a clothes closet. So we have to be careful there.
Ooh.
So, yeah, there's rules for clothes closet, but not for other closets.
What does 100 say on closets?
100 for closed closets is a non-habitable room or space intended primarily for storage of garments and apparel.
Does the code actually use the word closed closets?
That's the defined term, is closed closets.
But does it use it anywhere?
Yes, 410.16.
But is there anywhere else that it uses closed closets? Because if it's not, then why is it 100? So do a search on maybe electronic search. You guys can look for the word closed closets. But
It's in this.
Yeah,
It's in
24D.
24D.
it is in 24.
Yeah.
Okay.
24D, right there.
Oh, okay. Such as closed closets. I'm sorry. I missed the last sentence in there. So you cannot have an overcurrent. This is, I know, guys, and I know myself included, you want to put a panel somewhere. In my master bedroom, my panel is actually in the master bedroom because I want it in my closet, and I actually was going to make a little room and call it an equipment room, so when I get my final, then I would just go ahead and put shelves in it later on, you know what I mean, and just call it an equipment room. And then once I get my final, put my shelves in there, and then I was all fine to work in it because I wasn't going to put clothes in there. I was just going to put shelves in there and pile it all up, and I could never got to the breaker. Thank goodness I didn't do that. But I thought, nah, I'm not going to play that game. So then I'm trying to figure out where I can put the panel board in the master bedroom side of the house. And I said, hey, babe, you mind me putting it behind the door? She goes, I don't care. I'm like, really? Oh, perfect. So I put it behind the master bedroom door, but then I had the carpenter finish it all up with a nice wood little panel enclosure because I could not put it in the clothes closet. Also, overcurrent devices, nor can you locate the service disconnecting means. They're not permitted to be in bathrooms of dwelling units, dormitories, guest rooms, or guest suites. I'm sure some of you guys had pictures somewhere showing panels right inside the shower. You know what I mean? And you're like, my gosh, how could you put a panel in the shower? I mean, like, didn't it, what, you know? Unfortunately, most of the stuff is done by men. You know, we're not that smart sometimes, you know, obviously. 240.81, circuit breaker indicating. Kind of like circuit breakers must indicate whether they're in on and off position. Well, we have nothing to do with that. You buy them, and it says on, off. When the handle is operated vertically, however, now we have control. The up position handle must be on the on position. Well, this bottom row is fine, but since these are operated vertically, that would be the code violation. I do remember this. You know, sometimes I'm sure those that are watching this DVD or watching this streaming and going to seminars and learning code or reading code, I vividly remember one time pulling service conductors into an 800 amp disconnecting means, and I wasn't the foreman, but I remember that the conductors were too short to go to the line side of the disconnect. Now I was really, really young in my career, and I'm thinking, what does it really matter? Just flip the baby upside down. And that's exactly, and I convinced the electrician to flip it upside down. You know what I would have done today? Just would have made a butt splice and made the extension. But I thought, no, you can't make splices in panels. Of course you can make a splice in a panel. You're not going to turn the stupid thing upside down. When somebody thinks they're going to turn it off, they actually turn it on. See, the key here is safety. People are in the habit of knowing you turn it off, you turn it off. Not that you turn it off and then you actually were doing what? Turning it on. On is up, off is down. Now, you could have it sideways. You know, that's not a problem. You want to turn it left and right. There's no issue there. It's only if you're going to be operated vertically. Let's go to 240.83 markings. Circuit breakers used as switches. Now, this is only if you're going to use the circuit breaker to actually turn the lights on and off on a regular basis. Circuit breakers used to switch 120 or 277 fluorescent lighting must be marked SWD, which is switching duty, or HID, high-intensity discharge. Circuit breakers used to switch high-intensity discharge must be listed and marked HID. You guys got to help me. Is there, Brian, you probably have more experience. Is there an industry where the habit is they go in and they turn on all the breakers, and that's how they turn on the lights?
Warehouses.
Warehouses?
Warehouses regularly.
Is that how it is? They don't have a single switch. Okay, so I guess you get so many lights, and it's all in motion activity, and then whenever you want to turn it
Well,
off.
it's done primarily because of maintenance. You have a bunch of lighting contactors as one option where somebody comes in and hits switches, or you just flip breakers, and breakers are a lot less maintenance than a lighting contactor.
Okay, so, and all this is saying is that if you're going to be using breaker as a switch, and you're switching fluorescent lighting, well, then it has to be marked switching duty, or HID, because when fluorescent lights turn on and off, especially HID lighting, when HID lighting turns on and off, I can't remember enough, but the inrush is huge. And a regular circuit breaker is not designed to be handling that kind of inrush. So you have to make sure you have a switch, circuit breaker in that case, that's identified for that. Victor.
Yeah, and a lot of manufacturers now are making electronic breakers that where their panel is electrically operated breakers that are designed for energy management kind of things. And all of those are have to be rated for this.
So as
Square
I never
meter.
thought about energy management. One of the ways to handle energy management is just turn off the breakers.
Yep.
Yep.
Now, can they turn the breakers back on again?
Yes.
Oh, so breakers can turn off and on.
Yeah. Each breaker is motorized.
You know, I didn't mention this, but AFCI breakers, Cutler Hammer, and I can't say Square D does or doesn't, but Cutler Hammer has a new breaker that you can press it and hold it for like 2 seconds, and then it flashes, and it shows you the last time it faulted, what the fault was. Was it a fault from neutral to ground? Was it a short circuit? Was it a ground fault? Was it an overload? We're getting devices that are very intelligent and very smart. And so we're seeing energy management to start working with breakers. So that's an exciting, fascinating field. So that's pretty cool stuff. I'm done with 240. Just lightly touch, get you started inside there.